Today we're going to continue talking about the electron configuration. So yesterday we talked about the fact that you have that we have different energy levels. Okay, first energy level, second energy level, and so on. We said that those are identified by the principal quantum number, which is 1, 2, 3, 4. And that also will correspond to the period on the periodic table. Okay, so if you're in the first energy level, that is going to correspond to the first period or the first row on the periodic table. As we move to the second row, we'll start filling in the second energy level. As we fill to the third row, we'll start filling the third energy level, and so on. Now, there's a couple of things that are good and a couple of things that are bad about this little circular diagram. Okay? What's something that is correct or something that is incorrect about this diagram? Okay, first of all, we're going to put the big X by the circles. Okay? They are not really circles. Okay, so sure enough, they are not really circles. However, what is good about this?
The levels are in specific sections.
There are specific. So a check plus for knowing that there are specific levels. Okay. And each level then has a sub-level, or has sub-levels. So each level has sub-levels. Okay, and those sub-levels are going to be, let's pick that one. Those sub-levels are going to be the S, P, D, and F sublevels. Okay? So for n equals 1, the only sublevel that we have is an S. Okay? For n equals 2, there's an S sublevel and a P sublevel. For n equals 3, there's an S, a P, and a D sublevel. For n equals 4, we actually have an S, a P, a D, and an F sublevel. And then, of course, levels 5, 6, and 7 actually are just copies of number 4. So we don't get anything new or different after number 4. It just repeats again with 5, 6, and 7. So each level has sublevels, and those sublevels are S, P, D, and F. And then I'm going to tell you that each sublevel contains orbitals. Okay, so each level has sublevels, and each sublevel then contains orbitals. Now then the question is, well, gosh, how many orbitals? Let's see. Let's switch that to purple for that one. And I'm gonna. Now my S sublevel can only contain one orbital. All right, but remember, each orbital can hold 2 electrons. So the S sublevel only has one orbital, but that's enough to hold 2 electrons. The P sublevel only has 3 orbitals. Remember, they were shaped like dumbbells, and it was in the X and the Y and the Z. Okay, and I'll show you the picture of that again in a minute. 3 sublevels for up to 6 electrons. D has 5 sublevels, 5 orbitals for up to 10 electrons, and then F has 7 orbitals for up to 14 electrons. All right, and so that's our levels, our sublevels, and our orbitals. Okay, and that is that. All right, let's see. Oh, there we go. All right. Again, an orbital is a region within an energy level where there is a high probability of finding an electron, specifically over 90%. Okay? And so that is what we're going to say about that. Here is our s orbital. Remember that it has a spherical shape. That does not mean that the electrons orbit in a circle. It means that within that spherical region, there is a 90% probability that you will find the electrons that belong in that orbital. Okay? So it is the probability of that. And then our p orbital, again, we have one in the x, one in the y, and one in the z, and they're kind of shaped like dumbbells. Again, that doesn't mean that the electron orbits in a figure 8. It means that the electron has a 90% chance of being found within that region of space for each orbital. And remember, each orbital can hold up to 2. So there's, if all of these were full, we would have 2 electrons almost certainly within that space, 2 electrons almost certainly within this space, and 2 electrons almost certainly with that space, all overlapping, all of these axes stacked together. Questions about that? We're feeling good? All right, we talked about this yesterday, so we're doing okay. Remember then that the D has actually 5 orbitals, 1, 2, 3, 4, 5, and they're starting to look a little different. And the F, it looks like something crazy has happened here. I don't know what it was, but we've got 1, 2, 3, 4, 5, 6, 7 possibilities of orbitals, and that is that. All right, let's see. We're going to bypass that page. And I want to spend a little bit of time here, because this is where we started yesterday in terms of making our way through. So let's just say, hey, what if Mr. Willis had a lithium atom? Now, this is where lithium is on the periodic table. You'll notice that it is. Let's see. I'll just put it right there. It's at atomic number 3, all right? And so if we, look in atomic number 3, what does that 3 tell us? That it has 3 protons, all right? Now, if it has 3 protons, how many electrons does it have? Also 3, very good, because it's there's no reason to believe it's not a balanced atom. Okay, if it's a balanced atom, then it will have the same number of protons and electrons, so there are 3 electrons. Okay, now we know that all the protons and neutrons are in the nucleus, right? And we know that the electrons then are scattered around the outside in these energy levels, in these orbitals. All right, and what I want to do is I want us to start assigning a particular location to these orbitals. So lithium is going to have 3 electrons. Now, I'm going to put the first one in a 1s orbital. You remember that our very first level, okay, level 1, has an s orbital. That's the only orbital that it has. It has an s sublevel, which has 1 orbital. Now, how many electrons can I put in there? Up to 2. So 1, 2. So I'm going to say 1s2. All right, and that tells me that in level 1, my s orbital contains 2 electrons. All right, except I need to get to 3. So where will I put my next electron? Well, I don't have any more orbitals on the and no more sublevels on the first energy level. So I need to go on to my second energy level. And in my second energy level, I'm going to start with 2s. And I only need it. Now, how many will the s hold? It'll hold up to 2, but I only need to put in 1. So I'm just going to mark that down. 1s2, 2s1. And I can see if I count and add 1, 2, 3 electrons in there. And this notation tells me where they are. 2 of them are in the 1s orbital, and 1 of them is in the 2s orbital. All right? How do we feel about that? Feel good? All right. Well, what if we had? Let's look at one over here. Let's see what's in 6A on that. Oh, oxygen. Everybody loves oxygen. Okay, I mean, you breathe it. So, how many electrons does oxygen have? 8. Okay. Let's see. So that was lithium. So now we're going to have oxygen. And I need to get up to 8. I'm just going to put my 8 up here to remind me. All right. Hey, first 2 are going to go in that 1s orbital. So 1s2. Next, I've got the 2s orbital, which can hold 2. Now, what did the second energy level have that the first energy level didn't? It has a p sublevel. Okay? And so so that is where we're going to begin continuing adding electrons next. So 2p 1, 2, 3, 4 is all that I need to add in there. So 1s2, 2s2, 2p4. And by the way, these little lists of numbers that tell where the electrons are, what energy level and what sublevel, and how many, these are called their electron configurations. Ooh, can I get it all in there? Yes. So this is called the electron configuration. All right. Now, here's what I want you to see. You see how if we look at the periodic chart, we see level 1, and it's got, well, an s orbital. And you remember yesterday that I drew a box around this, and I said, hey, this little block represents the filling of the s orbitals. And this little tan block represents the filling of the p orbitals. And this little blue block represents the filling of the d orbitals. And this light green block here at the bottom represents the filling of the f orbitals. All right? So I'll tell you what, let's just try out, let's move to this one. I think that's, is it cobalt or is it iron? Let me see. Hang on. Which one did I pick? 1, 2, 3, 4, 5, 6, 7. Seventh one over is going to be cobalt. 1, 2, 3, 4, 5, 6, 7. Sure enough. Okay. So here we've got cobalt. All right. I've got cobalt, and I'm going to just real quickly erase these little lines from earlier. Okay, so now we are going to fill in cobalt. Let's see, cobalt. What's its atomic number? 27. Okay, cobalt is 27, which means it has 27 electrons. All right. And so I'm going to start putting them in the first shell, and that gets us through 1s2. What's next? 2s2. Diego, you are doing great. I'm going to put you on pause just for a minute and see if anyone else knows. After 2s2, 1, 2, Then I'm going to be filling in this level because I'm counting my electrons all the way down to cobalt. All right. So what level's next? We filled in level 1s. We filled in sublevel 2s. What's next? 2p. How many will it hold?
6.
Up to 6. And we got to get to 27, and we're not there yet. So yeah, 2p6. Now we're under the third energy level. What's going to be next? I'll give you a hint. Look at these letters here.
3s.
Yeah, 3s. How many will it hold? 2. So 3s2. And then next we skip across and we're going to fill in 3p6. We're still going because we're not all the way to 27 yet. Hey, now wait a minute. I happen to remember that in the third energy level, that's when the d orbitals show up. Or excuse me, the d sublevel with the d orbitals. So you would think, hey, we need to fill in the 3d next, right? Except here's the problem. That 3s and that 3p already have 8 electrons in there. And remember that like repels like, okay? And so you've got all those electrons, and they are repelling each other. They are pushing each other around and away, and there's force between them.
Like what? Home light reflect.
Like repels like.
Oh, I thought you said light.
No, opposites attract and likes repel.
Oh.
Okay, so all those negative electrons are repelling each other. Now, here's what that means. That means that it's actually less energetic and easier to fill in the 4s orbital before we begin to fill in the 3d orbital. Everybody okay with that? All right, so after 3p6, we're actually going to go on down and begin the fourth level. 4s, and I can fit 2 in there. Now I'm going to start filling in 3d. And I'm going to fill in 3d 1, 2, 3, 4, 5, 6, 7. 3d7. All right, and that's the electron configuration for cobalt. Yes, yes? We feel good about that? These are getting kind of long. Okay. Hey, let's do
Can we do francium?
no, we're not going to do francium. Hey,
Can we do
how
silver or
about
gold?
how about let's see, silver or gold? Let's see. I don't think I want to do gold. I want to do silver this time.
Okay.
Hey, here's the deal. Silver 47. I'm not excited about writing all of this all the way up to 47. Okay? Hey, let me come back to cobalt for a minute. Before we do silver, I want to do one more. I'm going to switch colors. Let's switch to indigo here. And I'm going to erase my lines. You got to hit the dots. That's trouble. All right. Whoop, go away, lithium. All right. Hey, I want to do this one. Is this argon? Yeah, argon. Okay, so I want to do argon. All right. So check this out. So let's do argon real quick. Okay. AR. 1s2. What's next? 2s2. Somebody else, what's next? 2p6. Excellent. What's next? 3s2. Next? 3p6. Okay, and that's it. That's it, right? That's argon. here's what I want you to see. You see this 1s2, 2s2, 2p6, 3s2, 3p6? That's the same as that start right there. So what if I take cobalt and abbreviated it argon, which I let stand for all this, and then I just pick up with 4s2, 3d7. Okay. Hey, that's a lot shorter. And what you can do is, for any spot on the periodic table, let's just say, okay, silver. Which one is silver?
It's 47 AG.
It's 47. Okay, so it's 2 over from cobalt. Oh, except I erased cobalt. Great. Okay, so it's one short of the end of the transition metals. Okay.
Oh, I thought you didn't erase cobalt or something.
Well, I erased it up here.
Oh.
All right. So there's silver. Now, here's the thing. Silver 47. All right. I'm not excited about writing and drawing all those arrows all the way down. Ooh, but what's right here? Krypton. So guess what I'm going to do? I'm going to put the noble gas krypton. Oh my goodness, that's not acceptable. Oh, whoa, that's really not acceptable.
It's a lot more room.
Yeah.
It is. I'm not gonna lie. I did like that real estate. Okay. I know. I was looking at that real estate. All right. Hey, there we go. All right. Here we go. Nice big bracket. Krypton. Hey, there we go. All right. Krypton. And then I'm going to start with 5s2. And then 4d9. 4d9. Hey, and that's not bad. I can write that. Okay? This is called the noble gas configuration. It's a shortcut of the electron configuration because you put the noble gas from the previous shell and then you just finish it out with the next row.
So it has to be a noble gas.
It must be a noble gas. You cannot just pick, hey, we're going to do silver, so palladium, and then just, one more electron.
Or like you can't get the second S and then just
Nope. It's got to be the previous noble gas. Yes, sir.
Is that because noble gases are neutral and won't lose or gain electrons?
Well, the reason that noble gases are neutral or inert is the technical word that we use. The reason they're inert or non-reactive is because their outer electron shell, their valence electron shell, is full. And so because they have 8 electrons in their outer shell, they are inert. And so that is going to make a complete, end of that energy level. And then we're ready to just go on to the next one.
So there won't be any ions for the noble gases?
No ions for the noble gases. Okay, they're not sharing electrons. They're not giving electrons. They're not taking electrons. Yes, ma'am.
Well, I have 2 questions. You said the word inert. Is that where the word inertia comes from? Because that sounds like a lot like inertia, inert.
You know what? They are going to have the same Latin root word.
Oh.
Meaning resistance to change.
Oh.
Okay. Because if it's inert, it's non-reactive. It resists interacting, and inertia is the same way. It's a resistance to acceleration or resistance to change in motion.
Also another question. Now, I remember doing this in 8th grade, though we had to do
Okay.
chemical symbols, like the whole yield thing, Like,
Yes,
actually-
we
she said-
will get
she-
to that.
She said they moved it to another year where like you had to balance it out though, and she said, do we do that here? Like, have to balance out the symbol?
We will get to that soon enough.
Like the reactant to the product or whatever.
Absolutely.
So say that, like, for example, you're about to do Krypton.
Okay.
You can still shortcut from Argon, or...
Okay, yeah, if you wanted to do Krypton, you could shortcut from argon.
Okay.
You can't say, hey, Krypton, hey, there we go, all right. You can't do that. You know, they want to, yeah. So that's that. All right. Let's see. Are there questions about the electron configuration and the noble gas configuration?
I'm about to write my notes.
We were going to write a couple more notes.
Okay.
All right. So what we're going to look at now is something called the orbital notation. Now, this is the electron configuration, which shows you the placement of the electrons. Now we're going to show you the orbital notation, which is about how the electrons fill the orbitals. Here's what I want to tell you about how the electrons fill the orbitals. Remember, okay, and I tell you what, we are gonna take just a moment now, and
Write down.
no, I'm gonna try to. How did I get it to jump over earlier?
Mm-hmm.
I know. And I'm trying to get the little slide bar to show up, and it's not.
Maybe try moving your...
Oh.
Yeah, that little bar.
Hey, there we go.
Free real estate.
Free real estate. All right. And I'm just gonna take cobalt. Okay, and I'm gonna slide it over here. Actually, let's start with a shorter one. Yeah, radon. Let's do radon. No. All right. We'll do oxygen. Okay, so I'm going to take oxygen, and I'm going to write the orbital configuration for that. Now, remember that first of all, I'm going to write the electron configuration: 1s2, 2s2, 2p6. Oops. I can't believe you guys let me do that.
We were waiting for you.
It was a test and you all failed because no one stopped me and said, Mr. Willis, wait, it's only 2p4. All right. So you will do better. Hey, check this out. Now, what we're going to do is I'm going to actually draw arrows to represent the electrons and specifically to represent their spin. Because you remember yesterday that we talked about that electrons, that in each orbital, you can only have 2 electrons, and that they must specifically have opposite spins. All right? Because of the magnetic fields, and the magnetic fields need to balance each other out. All right. So, 1s2. Now, the s orbital has, we've got an s orbital, and it can hold 2 electrons. So we're going to represent one with upspin and one with downspin. All right, great. 2s2. Again, 2 electrons. One up, one down. Now, we are on to 2p. The p orbital actually has 3. Remember that, the p sublevel has 3 orbitals? You remember that? Okay, at least the p sublevel has 3 orbitals, one in the x, one in the y, one in the z, right? The little dumbbells. Okay. Now, so I've got those 3 orbitals, and I'm going to put 4 electrons in them. Now, do you think that I'll go up, down, or do you think that I'll put 1 in each and then add a 4th somewhere? Oh no, Diego, no, it's not, shrug our shoulders and as if it doesn't matter. It matters. Oh, it matters. Diego, what do you know about electrons and other electrons? What do you know about electrons when they get together in groups? They what?
They don't like each other.
They don't like each other. They repel each other. So Diego, they are going to fill in singles. This is kind of like if you get on the bus, all right? If there's 10 of you and you get on the bus and there's 10 seats, nobody's doubling up or putting 3 people in a seat, okay? Everybody gets their own seat, all right? Now, what happens when person number 11 gets on the bus? Oh. Yeah, you kick them out, you close the door, you're like, no room for you. No, when person number 11 gets on the bus, somebody's got to double up. All right, hopefully there's 2 freshmen and you make them sit together. All right. Hey, and so 2p4, up, 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 down. All right. In other words, you put 1 electron in each orbital until each orbital has 1. Then you come back and double up. All right. Someone asked me earlier, Mr. Willis, why is it important to be able to show the electron configuration? Specifically because these unpaired, you want to be able to show whether there's unpaired electrons or not. That actually is going to have an influence on the physical and chemical properties of the element, whether it's magnetic or not, how it reacts with others, and so the unpaired electrons are important. All right, hey, let's look at cobalt. All right, just for fun. It's so much fun. Let's get a new. Let's see if the yellow is. Let's see if we can even see it. Yeah, can y'all see that? Yeah, that's a mustard yellow. It's okay. Or gold. So 1s2. So hey, I'm just gonna 1s2. I'm gonna put. Okay, up, down. 2s2. Whoops. Up, down. 2p6. Ooh. Up, up, up. Down, down, down. All right, and all of that is the 2p6 orbital. 3s2. Up, down. 3p6. Uh-oh. How did we do this last time? There we go. All right, 3p6. 1, 2, 3. All that represents 3p6. Up. Let's see. We got to fill them all in, so I'm just going to go ahead and. No, I should do it the right way, Diego. Down, down, down. All right, 3p6. 4s2, my goodness. 4s2, up, down. And then 3d7. Let's see, that's 4s2. Then 3d7. The D has 5. So all of this is 3d. 1, 2, 3, 4, 5, 6, 7. 3d7. All right? And so that is the orbital notation for cobalt. All right? Questions about that? All right. Good, because there it goes. It's gone. Hey, right here, orbital notation. Let's take a look. This happens to be for period 2 going across. Lithium. 1s2, 2s1. There's 1s2 up, down. There's 2s1 up. Up, down, up, down. Up, down, up, down. Up, down, up, down, up. Up, down, up, down, up. Up, down, up, down, up, up. Up, down, Up, up. Up, down, up, down, up, up, up. Up, down, up, down, up, up, up. All right. I know. I feel like we should be reading "Go Dog Go" now, or something like that. Say what? Cheat codes? Oh yeah, yeah. It turns out that the orbital notation of fluorine is actually the way that you get extra lives in. No, yeah. So no. That would be hilarious if someone actually did, the orbital notation of cobalt to get extra lives on something.
That would actually be very clever.
I know that would be hilarious. Okay, hey, we're moving on. Last thing for today: Lewis dot diagrams. A Lewis dot diagram is used to show the electrons, the valence electrons that an element has. So this is about valence electrons. We are going to put the element symbol in the middle. Put the element symbol in the middle and the electrons are on the outside. All right, so element symbol is going to go in the middle, and the electrons, and the valence electrons around the outside. Okay? Sure, no problem. Everybody take a moment, get that recorded. All right. So, for example, lithium.
What's that word after middle, like?
And the electron and the valence electrons are on the outside. So that little symbol is and. All right. So if I had lithium, I would write Li as the symbol for lithium. Hey, let's find lithium on the periodic table. All right, it's atomic number 3. In this case, I'm actually less concerned about its atomic number than I am its family group number. It's in group 1A, which means it has how many valence electrons? 1. Okay, so group 1A has 1 valence electron. So I take lithium and boop, and I put 1 electron around it. And that's all there is to it. I know, thank you very much. Thank you. Hey, let's see. Now, what if I did, what if I did boron? All right, excellent. It's in group 3A, so it has 3 valence electrons. 1. Oh, now do I put 2, do I double up? Why? What do we know about electrons? They like their own space. Okay?
Why don't you do iron next and in like the B section?
Ooh, I'm not going to do iron. Here's what I'll tell you though. Because it's in the B section, I'm not going to do iron. Because I don't want to. Hey, here's iron is. I'm sorry that ever. Hey, Eliana, the reason I'm not going to do iron is that iron, because it's in that B section, because it's a transition metal, it has some special rules to it.
Oh, okay.
And we are not ready to learn those special rules yet. And so that is the reason that I'm not going to do iron. Okay, that's the only reason.
Okay.
All right.
Training for whenever we do learn it?
Huh?
Don't we need training for whenever we are going to learn it?
I tell you what, we'll learn it on the day that we learn it. That'll be perfect. That'll be just enough training on that day. Hey, so let's press on with oxygen. I'm glad that you all are enjoying class. Glad we're having a good time. Hey, oxygen, how many valence electrons? 6. So 1, 2, 3, 4.
And then sandwich in between.
And then I'm going to start putting them on the sides 5. And instead of putting these two next to each other, I'm actually going to put it over here so that they can be as far apart as possible. 5 and 6.
It kind of looks like a face if you look at it real close with two little arms.
Sort of does. All right.
Neon next?
Let's do fluorine next. So fluorine, 1, 2, 3, 4, 5, 6, 7. All right?
Does it matter which side?
No, it does not. It does not matter which side is the lone side. Neon. And I'm just going to hit them as we go. 1, 2, 3, 4, 5, 6, 7, 8. Happy times for neon. Anyone else want to ask me to do one that I'll tell you no about? All right, which one do you go?
What about the ones at the bottom?
Uranium.
If I'm not willing to do a transition metal, I'm sure not willing to do a lanthanide or actinide.
Oh, okay.
Hey, how about barium?
Oh,
Perfect, barium. Hey, Ba, what group's it in?
6.
That's period 6.
My bad, 2.
It's in 2.
It's in group 2, which means we're gonna put 2 electrons, and I'm just gonna put them right there next to each other. You could put them across also. It'd be fine. All right. Hey, questions about the Lewis dot diagrams? It's just a pictorial way to show valence electrons, and we will come back to it when we talk more about bonding. All right. We're going to stop there for today and do a little practice.